Good morning, students. Today we are going to discuss our second chapter of physics, which is electrostatic potential and capacitance, in which first we will discuss about electrostatic potential. The electrostatic potential at any point is in the region of electric field is equal to amount of work done in carrying a unit positive test charge from infinity to that point against the electrostatic force. Mathematically, it can be written as V is equals to W upon Q naught. The SI unit of potential is joule per coulomb or volt. Electrostatic potential of a conductor is the electric state which determines the flow of charge when the given conductor is connected to other. Positive charge always flows from a higher potential to a lower potential, while the negative charge always flows from a lower potential to a higher potential. It happens until the potential of both the conductor becomes same. Now here the definition of 1 volt. If 1 joule of work is done in carrying a test charge of 1 coulomb from infinity to a point in electric field, then the potential at that point will be 1 volt. Now our next topic is potential difference. The work done by an external agent in carrying a unit positive test charge from one point to another point in an electric field is called the potential difference between those points. Suppose we want to displace a test charge from B to A, then the potential difference will be equal to VA minus VB, which is equals to W upon Q naught. Now the next is electron volt. Electron volt is defined as the amount of work done in carrying an electron from infinity to a point where the potential is of 1 volt. So 1 electron volt is equals to 1.6 into 10 to the power minus 19 joule. Coming to the next, electric potential due to a point charge. The potential at a point is given by V is equals to W upon Q naught, where W is the work done in carrying the unit positive charge from infinity to a point in electric field. So on solving this, we will get a formula V is equals to 1 upon 4 pi epsilon naught Q upon R. This is the formula for electric potential due to a point charge. Potential is a scalar quantity. If there is a group of point charges, then for calculating the total potential at point P, as in the diagram, we will calculate the potential at point P due to various charges Q1, Q2, Q3, Q4, and for calculating the total potential at point P, we will algebraically add all these potentials, or it can be written as V is equals to 1 upon 4 pi epsilon naught sigma I is equals to 1 to n Qi upon Ri. Now our next topic is electric potential due to an electric dipole. For this we have two situations. First, on the axis of a dipole, let AB is a dipole, and from the midpoint of a dipole a point P is situated at r distance. For calculating the electric potential due to that dipole, we have to calculate the potential due to charge positive Q and due to charge negative Q, and for calculating resultant potential we have to add them, and we will get a formula V is equals to 1 upon 4 pi epsilon naught to LQ upon R square minus L square. On considering a situation in which R is very far than L, or R is very greater than L, we will get V is equals to 1 upon 4 pi epsilon naught P upon R square. Now our next discussion is the electric potential due to an electric dipole on equatorial line of dipole. For calculating the potential at point P, we have to calculate the potential due to charge Q and due to charge minus Q. On solving these potentials and calculating the resultant potential, we will get V is equals to 0. Now our next topic is equipotential surface. A surface over which the electric potential is same everywhere is called equipotential surface. Here I have mentioned some properties of electric potential, and the first one is no work is done in moving a charge between any 2 points on an equipotential surface. This is because the potential difference is 0, so W is equals to Q delta V, and delta V is equals to 0, so W will be 0. The second property is the electric field and the lines of forces are everywhere right angles to the equipotential surface, and the third property is that no two equipotential surfaces can intersect each other. Our next topic is potential energy of a system of charges. Here is an example of two charges. Suppose Q1 and Q2 are placed in vacuum at a distance r meter. Then the potential at B due to charge Q1 is V is equals to Q1 upon 4 pi epsilon naught r. Then work done in bringing charge Q2 from infinity to point B, W is equals to Q2 V, which will be equal to 1 upon 4 pi epsilon naught Q1 Q2 upon r. This work is called electrostatic potential energy of the system, or it can be written as U is equals to 1 upon 4 pi epsilon naught Q1 Q2 upon r. Now our next topic is potential energy in external electric field. Suppose there is a single charge, then the potential energy of that single charge will be equal to Q dot Vr, where Vr is the potential at that point due to external electric field E. If there is a system of two charges, then the formula for electric potential energy will be equal to U is equals to Q1 V1 plus Q2 V2 plus Q1 Q2 upon 4 pi epsilon naught R1 2, where Vr1 is the potential at R1 due to the external field, Vr2 is the potential at R2 due to external field. Now next topic is potential energy of a dipole in an external field. In a uniform electric field, dipole experiences no force, but it experiences a torque. Tau is equals to P cross E. Let the torque is applied to dipole so that it rotates from angle theta naught to theta 1 with respect to the electric field. Then the amount of work done by the external torque will be equal to W is equals to integration theta naught to theta 1 tau theta d theta. On solving, we will get Pe cos theta naught minus cos theta 1. This is the formula for potential energy of a dipole in an external field.